Anyway, so I will talk about some methods for dealing with missing data, and I have this listed under 4 headings, and you can read them. It's first useful, I think, to know when missing data can actually be ignored, because then it suggests the sorts of corrections that might be needed, or estimation methods that have some robustness properties that others don't. So if we start with the linear model, and to just allow some generality, consider estimating it by instrumental variables. So think of equation 1 as being a random draw from the population of interest, and then we may or may not observe all of the data that we need in order to estimate this equation by either 2-stage least squares or actually even some sort of generalized method of moments procedure. Actually, to illustrate the main idea, just assume that the model is just identified, so we have the same number of instruments as regressors. So you can write the instrumental variables estimator as in equation 2 and then substitute into equation 3. And we've seen indicators that indicate missing data before. One certainly is in the treatment effect literature, where for the people who actually become treated, we have missing data on them because we don't observe the counterfactual in the state where they're not treated. So I'll actually have a little bit to say about how some of these methods apply to that case. Guido's covered it, of course, quite well, but I'll have another couple of comments to make, perhaps. So the instrumental variables estimator, written in terms of the errors and beta, can be written like that. And the selection indicator SI simply just takes out the data points that we actually observe. And then the way to think about this is, in general, we should just think of SI as being random, because we don't really know why a particular observation is observed or not. This might be data that's just missing on Y. There might be a covariate that the data are missing on, or some combination. It could even be that we're missing data on the instrumental variables. Okay? So the question is, using this simple representation, when would using what they call in the statistics literature the set of complete cases, when would that produce a consistent estimate of beta? And the weakest condition is given in 4. That's just follows by looking at the final average in equation 3 and asking when would it have a probability limit of 0, and then, of course, by the law of large numbers, that's exactly when the expected value of the a generic element is equal to 0. And so this is it's a kind of zero correlation assumption, but it's not zero correlation in the population. The selected sample the selection indicator matters here. So a sufficient condition, of course, would be to assume that the error term has a 0 mean conditional on the instruments and selection. And then a special case of that is that in the underlying model, the error term has a 0 mean. So this is an assumption purely on the population. And then what would suffice is that selection is based on the instrumental variables. Okay, so that means a deterministic function of the instrumental variables. Notice, of course, in general, that it can't be a function of the regressors, because if those regressors are endogenous, then that's going to violate this condition. So the general, everybody pretty much knows this, I think, that the idea is that if the sample is selected on the basis of exogenous things, then that doesn't cause any systematic bias in estimating the parameters in the population model. But it's a little important to be formal about that, because notice that while this is sufficient, along with selection being a deterministic function of the instruments, it's actually not sufficient if we just impose the 0 correlation assumption, which is the one we often use to motivate instrumental variables estimation. So in other words, even if selection is a deterministic function of z, whether it's linear or not actually, because this s times z is not going to be a linear function. Zero correlation is not generally going to be enough. Now, the case where this would be enough is if selection is independent of everything, right? So if selection SI is independent of the instruments and the errors, then that expected value is, of course, the product of the expectations, and then we're done. So this distinction actually comes out in the statistics literature, and I'll talk about these definitions a little more formally later, but if selection is independent of everything, that's typically called missing completely at random. And when selection depends on some observable things, that's, in this case, the exogenous instruments, that's a case of missing at random. In this case, I think we would just call this exogenous selection, and that pretty much tells us what's going on. By the way, this distinction between zero correlation, in this case, and zero conditional mean, this actually does have some implications about whether one wants to use so-called weighted estimators that we're going to talk about later on, even in cases where the selection is a function of exogenous variables. Okay, a special case, of course, is, let's go there. A special case is where we've modeled the conditional mean correctly. It's a linear function of the x's, and then, of course, selection can be a function of x in any way, with the slight requirement, of course, that we have enough variation in the x's so that we can actually estimate the regression function. Now, this kind of derivation extends in a fairly straightforward way to most estimation methods that we deal with. It's easiest to state the assumptions differently depending on what the population object of interest is. So in the case generally of nonlinear least squares, this would be the sufficient condition to ignore selection. If we're doing quantile regression, it would be that the median of or least absolute deviations, which I'll talk about later today, that would be the condition. And then if we're doing maximum likelihood, it's a conditional independence assumption. So in all these cases, you can see that selection can be a function of the conditioning variables, but what it rules out, of course, is selection that depends on the response variable that cannot be explained by the conditioning variables. By the way, showing each of these is easy. In fact, you do it pretty much in one general framework, because in each of these cases, we know that the mean, the median, and the density, or the log density to be more precise, solve an optimization problem in the population. The true parameters either maximize or minimize an objective function that leads to either least squares, least absolute deviations, or maximum likelihood. And so basically the argument is shown in a few steps. I work it through in my textbook, for example. But anytime you can show that in the population you have an objective function that identifies the population quantity of interest, well then multiplying it by a selection indicator and then taking the expected value and using iterated expectations gives you the result. So there's nothing special about these three except that they happen to be common estimation methods that we use. But something like Poisson regression, which we know is fully robust as long as you have the conditional mean correctly specified, would also fit into this category for exactly the same reason, that the mean maximizes the expected value of the quasi-likelihood function, and it doesn't have to be that log likelihood function is correct. Okay, so clearly if we are interested in estimating unconditional moments, like just the mean, and we try to use the selected sample, then that's going to require that the mean is the same in the selected subpopulation and the unselected subpopulation. And Guido talked about how, of course, you can come up with bounds on these sorts of things if you have a bound on the variable y itself. Okay, now with panel data, exactly the same sorts of things hold. Just to consider the case of maximum likelihood, or I should say partial maximum likelihood estimation, then again we can write this in a couple of different ways, but the point is that conditional on whatever the x's are, selection is independent of the outcome. And again, the way one goes about showing that this is sufficient is to look at the so-called pooled likelihood function. Now notice in this case, this is not necessarily a true likelihood function, because this might not actually represent a joint distribution of the response variable across all time periods, conditional on the x's at all time periods. So this is applicable to lots of cases where we might be using panel data, but we're interested in something like a static probit model, say, or we've put in some lags for a distributed lag model, or even cases where we might have lag-dependent variables, but we also have explanatory variables that might not be strictly exogenous. In all of those cases, you can't write down easily a joint likelihood function. But all that matters is that we're interested in this conditional density. We have it correctly specified, and that being in the sample at time t for unit I is conditionally independent of whatever the response variable is. Okay. Intuitively, this, I hope, makes pretty good sense, and again, the argument about how that goes through is sketched out here and covered more extensively in the notes, but it does allow for some flexibility. Of course, if we go back to this condition down at in equation 7, the more that's in x, clearly the more likely this assumption is likely to hold, because if x is empty, then we're basically assuming that selection is independent of y. That is what the assumption is. If x has, say, lag-dependent variables and other observable variables in it, or at least partially observable variables, then this allows selection to depend on whatever is in x, okay, as long as it doesn't also depend on y at time t once you condition on x. So as you go from models such as static models to models with dynamics, it's more likely that you're going to be able to ignore the selection problem, which in this case, in a panel data case, it might be attrition, units dropping out. It could be attrition where units drop out and you never see anything about them, or it could be people moving in and out of the labor force and you're trying to model labor earnings or something like that. So at this level, this is fairly a fairly general statement. But of course, if what happens is that selection is a function of shocks that occur between time t minus 1 and t to yt, then this condition is going to be violated, and that's why we typically then worry about attrition, say, in panel data, and we worry about people moving in and out of the labor force in a non-random way. Okay, so again, that's a fairly general result, and again, you can see that this would work if we replace this log likelihood function with a squared residual function. Then you can easily write this down in terms of expected values as well, where you're using nonlinear least squares. Or you could do the same thing with a dynamic, say, least absolute deviations regression. Okay. So as I said, this is if we do have a lag-dependent variable, then it does allow selection to depend on y. We don't have to have that. If we, in any case where we think that it really is just a matter of, say, rotating people out of a panel exogenously, then of course it shouldn't matter that we are getting different samples on people at different time periods. We should be able to ignore that, assuming, of course, they all come from the same population, and that is implied by this general, very simple result. Now, unfortunately, it's much more difficult to write down conditions in general nonlinear models when you have unobserved effects. Because, of course, if selection is truly independent of everything, then that's easy, because then anything you do, whether it's maximum likelihood where you have some way of removing the heterogeneity, such as in a so-called fixed effects logit or fixed effects Poisson regression, then in those cases, actually, selection can depend on the heterogeneity because you have a way of eliminating it, basically. But in cases where we don't have good ways of removing heterogeneity, which is that entire class of models I talked about on Monday, where you model the heterogeneity as some function of the, say, the time averages of the covariates or other functions of the covariates, you would have to assume that basically selection is a function of those observable things, that what's left over doesn't cause selection. And that's a little unsatisfying, because that leads to basically selection on things that are exogenous, and we don't necessarily think that's always a good characterization. So in general, although there are special cases where one can remove the unobserved heterogeneity and then allow selection to be a function of that heterogeneity, in general that's complicated. But I will work through the linear case with unobserved heterogeneity, just so we can make sure we understand what is allowed and what's not going to be allowed in these cases. Okay, so if we start with this model with, again, time effects and then the additive unobserved heterogeneity, again, thinking of cases with a large cross-section and small number of time periods, and we want to allow for general correlation between, well, actually, in this case, instrumental variables and the heterogeneity, then it makes sense to remove the heterogeneity before using some sort of estimation method. And so we can think of a couple of assumptions that we'd be willing to make, maybe. One is given in equation 11. Now, this is never the weakest form of the assumption that you can write down, but I think it's probably one of the easiest to interpret. This says that the idiosyncratic error at time t, and then this is just the usual conditioning on the exogenous variables in all time periods, but then also conditioning on selection in all time periods, that's equal to 0. Okay, so this is a very clear sense in which selection in any time period is not allowed to depend on the idiosyncratic errors in time period t. So this rules out, for example, the idiosyncratic errors reacting at time t to somebody dropping out at time t minus 1. It also rules out people dropping out at time t plus 1 based on what happened to them in time t, at least if we don't observe the things that happened, which namely are in UIT. Now, what this doesn't restrict is this doesn't say anything about the relationship between selection and the unobserved heterogeneity CI. Okay. This next assumption does make that restriction, because it basically says, in addition to the standard random effects assumption that heterogeneity is at least mean independent of the exogenous variables, it's also mean independent of the selection indicators. So this is more of a random effects type assumption. This is more of a fixed effects type assumption. Actually, random effects typically uses both of these. Well, it does use both of these, although, as I said, you can relax this a little bit. And so this is certainly more likely to be true on its own than adding this along with it. And so if we use fixed effects on the unbalanced panel, that means we can get by with this, okay? Because what happens is the time demeaning now happens, well, it still happens, of course, within each I. It's just that we can only subtract off means of the observations we actually have. So in this notation, t sub I here, it's properly considered a random variable, right? It's the number of time periods we observe for unit I. And since we're allowing selection to be random in any time period, then the number of times any unit is in the sample is random. So if you make these definitions, then you can write down the so-called fixed effects IV estimator in this form. And then if you do the simple algebra to get it in terms of the errors, you can see that the weakest condition for consistency is this right here. And again, it's not enough just to say that the ZIs are uncorrelated with the U's. Hidden, this notation, I suppose, is a bit misleading, because hidden in this ZIT double dot is a function of the instruments in all time periods. And of course, that means that the selection indicator is hidden in there as well, in a nonlinear way, actually, because we're dividing by 1 over the number of time periods for each unit. So this is a nonlinear function of selection and the exogenous variables. So you could just assert this, of course, but then you're thinking about, well, when is this going to be true realistically? And basically it's that the idiosyncratic errors are not correlated with selection in any time period. Okay? And then it restricts the exogenous variables as well. Okay, so if we were to do, let's see. Oh yeah, one important point is that this all hinges on this structure where we have this additive unobserved heterogeneity. So remember back to the first lecture, I gave a set of conditions under which the fixed effects IV estimator on a balanced panel would actually be consistent for the average effect under what is not a completely general assumption, but is a somewhat reasonable assumption, at least for continuous endogenous variables. Well, unfortunately, one of the problems with unbalanced panel is that if you just relax the assumptions of the basic model a little bit, and now let's say we add random coefficients instead of assuming a constant beta, then the condition that would be needed for consistency, well, you can write stuff down, but the only thing that would make sense is this doesn't depend on the Z's and the selection in any time period. So if you are worried about that this unbalanced panel would cause one not to be able to consistently estimate the average effect, then it's easy to come up with some sort of test for it. There's no claim that this is somehow the best test for it, but consider this as an alternative where we don't worry about the exogenous variables because we might very well just be thinking of them as independent of the slope coefficients anyway, and we're focusing on, is there a selection problem as it relates to being correlated with these individual specific slopes. And so as a simple way to come up with a test, it seems to make sense to specify that as an alternative. And because we have a large cross-section, we're assuming, and relatively few time periods, of course, we should have units with all time periods, TI. Now, we can't do anything with the units where we only see one time period because we don't have any way of removing the heterogeneity for them anyway. And in the formula, they just drop out. Okay, so one way to implement a test is to take the set of individuals where we have a complete set of data as the base, and then essentially define interaction terms for all the other possibilities, and then just add these as explanatory variables to the equation where, of course, these x's, if they were endogenous before, they're still endogenous, and so this equation should be estimated by instrumental variables. But we have instruments for them because those would just be the ZITs interacted with the same sort of selection indicator. So that's just one simple way to come up with a test for selection problems. The same thing is true if we difference, and we'll actually, in the notes, I discuss this case in more detail because For attrition problems especially, differencing has some advantages because if attrition is an absorbing state, then you know if you see a unit at time t, then you also see that unit at time t minus 1. And so differencing becomes an attractive transformation relative to the within transformation, and you can do some more things with that you can't do with so-called fixed effects. Okay, so here was the comment. I guess I should have saved it, but it's difficult to handle general models with nonlinearities in the unobserved heterogeneity. And I think almost nothing is known, or at least not in any classical setting, where you can deal with dynamic nonlinear models with unobserved heterogeneity. The methods that we have, except in special cases, really rely on having a balanced panel. Okay, so if we think we need to do something about missing data, what can we do? Well, I'm going to start talking about inverse probability weighting, and in the cross-sectional case first. The idea, of course, is to try to re-weight the sample that we observe to make it reflect the population. And the question is, when does that sort of reweighting work? Well, we already talked about what would happen if we tried to use the mean just on the data that we observe, and that would require selection to be independent of the y's themselves. The general approach to this problem usually uses what's known as a selection on observables assumption. This is a special case of the so-called missing at random assumption, where instead of saying that selection is independent of y when we want to estimate its mean, the assumption is that selection is independent of y conditional on z. Now, this is not necessarily a convincing assumption in lots of cases. So it's important to understand that a lot of methods actually rely on this assumption, or even things that are more complicated than it. Inverse probability weighting relies on it, as do imputation methods that we're going to talk about a little bit later. And so, it may be that this is just a non-starter, and so when you get sampling weights and so on with your data set, instead of just using them as if somehow they've come from some really sophisticated underlying information that we don't have access to, you might be a little suspicious, actually, that one set of weights is being offered to solve any kind of missing data or stratified sampling problem. But in any case, this is a reasonably popular thing to do, so let's go ahead with it and see the kinds of problems it's been applied to. So the idea is to just, this is, I think, the easiest way to think about what's being done that essentially shows immediately why this works. Notice that this average here is over all of the potential observations. So in other words, you think of drawing randomly from the population, but if SI is equal to 0, for whatever reason, you can't use that observation. So the SI selects that out. And then we weight by 1 over the probability of observing the observation conditional on whatever the ZIs are. And it's of course, it's easy to show under this assumption that what this weighting does is if you take the expected value of this, you get mu sub y. And it's an application, not surprisingly, of the law of iterated expectations, and then using this condition here. So it's actually quite simple to show that. Now, occasionally you actually know what this probability is. And one case where you know this is in variable probability stratified sampling schemes, where ahead of time some sampling probabilities are decided, and then you say do a telephone survey and you keep an observation with a certain probability. In that case, you actually know these. But in general, they have to be estimated, such as in any scheme where you just are trying to model why some data are missing as a function of data that you actually observe. Okay, so in practice, this is what you do where the p-hats are estimates. And writing the equation like this, makes it, I think, a little more relevant for practice, because N1 then is just the number of data points that you actually have. Okay? And then this ratio here, this rho hat, is the fraction of observations that were kept overall in the sampling scheme. And so this is often the thing that's reported as the sampling weight, okay, where this can be bigger or less than 1 depending on whether the observation had a higher or lower probability than a generic observation. Okay, for actually studying the properties of the estimator, this is a more convenient formulation. Okay. Okay, and of course, this is just a consistent estimate of that fraction of kept observations. You get a somewhat different answer by setting this up as a weighted least squares problem, because now the sum of these things actually show up as in the weights, but the how one analyzes these estimators is quite similar. This is actually the formulation that is used for doing regression analysis. So we'll talk about how one does regression analysis in this framework shortly. Now, there are some problems with inverse probability weighting, and I alluded to them already, but there are some problems that are perhaps a little more subtle than what I said, which is that we're assuming that selection actually doesn't depend on the thing we're missing data on. We're assuming it depends on other things that we're not missing data on. This actually comes up in a paper by Horowitz and Mansky, where they studied a fairly simple problem, which was estimating the mean of some function. So whether you call this, you could just redefine this to be y, of course, instead of having it be g of y. But the key is that it's conditional on some other variable taking values in a certain set. So you can call this, I guess I didn't actually write that here, call this the dummy variable d, which is 1 if x is in the set and 0 otherwise. So x could just be something like a gender indicator, and then you want to estimate the mean of something such as earnings for women versus men, for example. And the caution that their paper is mainly interested in providing bounds that you can find, and Guido talked about this actually. But they do mention a problem with these so-called probability-weighted estimators, and that is that in your sample, you usually find weights that are supposed to estimate this. And in fact, this is the rho hat that I talked about, and this is the p hat as a function of z that I talked about. So those are the weights that are reported with your data, where sometimes we don't know what z even was. Okay? But the point is that if we don't know what z was, then we don't know that x was actually included in z. And if you use the probability weights that you get, you actually might come up with an estimated mean that is outside the range of possible values that any logical bounds analysis would come up with. Of course, if this function g of y itself is unbounded, then that's not possible. But in other cases where, if y is a binary variable, for example, then you can come up with estimates that lie outside the bounds, the Horowitz-Mansky bounds that are based on no assumptions at all. Okay, so the solution to this is to basically always make sure that whatever you're conditioning on here is used in calculating the weights. Okay, so this should be conditional on this event, and this should be conditional on this event as well. Okay, then that solves the problem. However, if you don't always observe x, then you can't put it in the conditioning variable z. Okay, so when you get these weights and you're missing data on some x's and you're missing data on some y's, then the weights weren't constructed using those, and you have to wonder, whether they can be used for all kinds of econometric problems. Now, there's a related issue here, and in that if the weights, say, depend again on variable z, and we want to apply regression analysis. So we'd like to estimate the parameters, say, in this population regression. Okay. And we have missing data on either y or x or both, but we want to use these sampling weights in order to do it's called a weighted least squares estimation, but it's with probability weights. We're not choosing weights that are 1 over the estimated variance of y given x. Okay, so the problem is, if we look at the solution to this, so that's written out like this, summed over all observations, and then again, using the same device to select out the observed data points. The problem is that if, in fact, selection is exogenous in this sense, okay, so suppose that selection is a function of the x's, which maybe, includes age or gender or something like that, and maybe we're missing data on those variables for some fraction of the population. But if this is true, then, as we just discussed, consistent estimation would be obtained by just ignoring the problem and doing least squares on the observed data. Okay. But if this is true, and x cannot be included in z because x is not always observed, then this condition is probably very unlikely to be true, because the selection, in fact, in a case where selection is a deterministic function of x, it's clear that this can't be true if x is actually not contained in z. So in other words, if we specify some set of variable z, and we go ahead and we estimate a probability of selecting the sample based on z, and then go ahead and do this inverse probability weighting, the weighted estimator will actually be inconsistent, okay, whereas doing nothing would have been consistent. So it's not as if sometimes you hear people say, well, of course, I should use the weights because that can't hurt, right? Well, it can hurt if the weights can't be a function of all of the right things. If in this regression context, if you can always include x in z, then the case for weighting is much stronger, because then it just becomes a functional form issue. Maybe you've thrown some things in z that you don't think belong in the population regression model, but would help to explain, the probability of being in the sample. Well, if only the x's matter, then if you make, with enough data and a flexible enough model, you will pick that out, and so in the end, you won't have an inconsistent estimator. But if you can't include x and z, then that's a different issue. Okay. So this theme actually comes up, unfortunately, in all of the methods that I'm going to talk about. The same issue comes up in imputation methods as well, because if the missing at random assumption doesn't hold, yet you're doing a regression and selection was largely on the basis of the x's in the regression, then it would have been better to not do the imputation, because that'll actually be inconsistent. Okay, I'll mention that again. Okay, now suppose that there's this issue of whether one should use weights if, in fact, we think that selection is what we would typically call exogenous in this case. And let's say we're doing linear regression. Actually, the same sorts of issues come up if we're doing nonlinear regression or maximum likelihood, too. The question is, should we use inverse probability weighting? Well, the answer is it depends. The answer is no if we believe 21 is just the assumption that the conditional expectation is linear. And then if we added the standard homoscedasticity assumption, then clearly we shouldn't weight, because OLS. Of course, if that isn't true, you can set it up to be true, right? You can always just force the data set so that attrition is an absorbing state. So, of course, if we can observe a set of stuff, in general, lump these variables together in something called WIT. Again, you can do maximum likelihood here. This could be a variety of other problems, least squares or least absolute deviations. if you can find variables RIT observed such that this is true, then the weighted, what's usually called the weighted maximum likelihood estimator is this. This is actually better called a weighted partial maximum likelihood estimator because, again, there's no presumption that that if we didn't have to do the weighting, that this would be a joint density function over the entire set of time periods. It's just modeling a set of conditional distributions. And generally this works because if you write the objective function like that, then what you can show is that its expected value, the expected value of the weighted thing is equal to the expected value of the unweighted thing not selected in the population. That's how these things all work. Okay. Well, the question is, how can, this is a strong assumption, right? Because if we're going to estimate these probabilities, the RITs have to be observed, or at least they have to be observed at time t. If you have general missing data problems, the question is how do you choose these RITs so that you have a chance of estimating a probability such that this is true. In the attrition case, the assumptions are strong, but at least you see some sort of natural structure that leads to a fairly simple approach. So the strategy that's suggested in this Robbins-Rudnitsky-Zhao paper is a sequential strategy. So the idea is to estimate a sequence of conditional probabilities where, so for the sake of argument, let's say we start off with a random sample in the first time period, and then what we have to do is figure out, estimate probabilities of why people are leaving at time t, conditional on being in the sample at time t minus 1. And of course, because of the way attrition works, these ZITs, they only have to be observed for everyone in the sample at time t minus 1. Okay, so we're moving along in time, and actually the ZITs are growing in dimension even though we're seeing fewer and fewer people, because we are going back, every time we go one time period more, we grab the person's, the units who are still in the sample at time t minus 1, we get their z's. So the idea is to model these sequential probabilities, estimate them, and then to form the probability weights. But these aren't the weights that you use at time t. We need to weight by the, if you will, unconditional probability of being in the sample at time t, not the conditional probability at being in the sample at time t minus 1. Well, this is where the assumptions really get strong. I'm writing down the simplest version of the assumption that makes it clear that the procedure works. The Robbins et al. Paper shows that some weaker set of assumptions do work. They focus on the regression case. So if you let v at time t be everything that is either in the population model and then this extra stuff, which generally would be lags of things that are in that model, then the condition is this right here. Okay? So that somehow we have good enough things at time t predicting attrition that none of the rest of the history of v matters. It's a strong assumption. Okay, so under this, you can show that, in fact, if you believe this, then the probability at time t, in fact, is just the product of these probabilities, these conditional probabilities. And so now the procedure is fairly clear. You just run a sequence of logits or probits or something like that, basically throwing everything you can think of into the probit or logit at time t that you observe for everyone at time t minus 1. You compute the product of these probabilities, and then these become the weights that you use in order to, quote, solve the attrition problem. You have to be a little careful. I have seen papers where I'm pretty sure they're actually weighting by these conditional probabilities instead of the product of them. Okay, this is the thing that falls out of this kind of framework. There are a couple of things that one should worry about. first of all, as a practical matter, these can be quite small, right? You're now taking products of probabilities, and so do you really want to give so much weight to observations where the conditional probability of being in the sample at each time period is small? Well, of course, the theory tells you should do that. Whether you should do it in practice is a different matter. There's this other practical problem which is very similar to what I talked about in the cross-section case, and that is if in fact it turned out that the selection is mainly due, or let's say entirely due, to the things you're conditioning on in your model, then this could just be a disaster. It could lead to inconsistent estimates when you didn't have to do anything except just use the attritted sample as is. And there's really no way to tell. That's right, because you can't always observe these X's. And in the attrition case, this is especially true, because attrition means they're dropping out. That means it's not just that you're not seeing the Y's, you're not seeing the X's either. So I did some theoretical work on this, and having thought about it more, it's not entirely clear that this is such a safe thing to do. Again, the argument that, well, it can't do any harm is not true, actually. It can do some harm. A related point is that if you start by assuming that your model is what some like to call dynamically complete. So in other words, if you have specified the distribution conditional on everything in the past, or say a conditional meaning you're doing least squares, this really reduces the role for weighting, okay? Because what sorts of things could you include in those attrition probabilities as you're moving through time? Well, they're things that you observe for people in previous time periods. But if this is your model, then selection by definition is a function of the things in the conditioning set. Now, whether your model actually contains all the Y's back to the first time period, that's not the issue. The issue is whether it represents this conditional distribution. And if it does, then you can't really make a case for doing the weighting unless you have some external information, like on people who were doing the interviewing in different time periods. That information clearly wouldn't show up in your underlying structural model, but may actually affect the probability of the person leaving the sample or whatever. So that's in those cases you can make a stronger case. But if all you're going to do is do a bunch of logits or probits conditional on things that could already be in your model, then it's not so attractive. Okay, imputation. So the first thing we talked about was just when can you ignore the problem? So that's the so-called complete case analysis. Then I gave you a quick run through on some ways that inverse probability weighting is used. But again, that uses just the data that you have, right? But it weights it to try to make it representative of the population. Another approach is imputation, where you actually try to fill in the missing data and then use it in some way in subsequent econometric procedures. So I recommend the book by Little and Rubin on this. It's quite accessible, and it actually, in the end, multiple imputation relies heavily on Bayesian arguments, and so and in fact Guido talked about a particular example of that in his talk on sampling from in the case of a censored Tobit model. So I think I'll just make a couple of points here. I suppose as with all methods, such as inverse probability weighting, it's better, it seems like, well, you're not just doing least squares or maximum. You're using these weights, and that seems kind of neat and so on. And so you kind of forget maybe that, what the assumptions underlying it actually are. I think there's a bit of this in the imputation literature too, because now, sometimes you get data sets that have 5 or 6 imputed samples, and you go, okay, I know how to deal with this. And there is a set of assumptions under which that the methods that have been worked out work. But the problem is that this missing at random assumption is key in making imputation work, just as something like it is key in making the inverse probability stuff work. So it doesn't, in the case where say we have a variable y, we don't always observe it, we do always observe some x's, then missing at random is basically this assumption here. Okay. You can define it for general patterns of missing data, but it gets complicated because you can only, the probability of a certain data point missing, a certain variable missing, can't depend on its value. It can only depend on the values of things you observe. So if you think about general patterns of non-response in surveys, this becomes very complicated. And that's why Bayesian methods are used to essentially do these simulation methods like Monte Carlo, Markov chain Monte Carlo methods are needed in order to essentially draw parameters and data at the same time. So I'll just, so for example, this is just that the probability of, say, retaining observation 1, let's see. Yeah, okay, so here, for example, the probability that the data on on W1 and W2 is both missing can't depend on what those values are. They just have to be some constant. So in a sense, this is this really seems like a missing completely at random assumption on when both variables are missing. So right away you can see that if you're going to allow general patterns of missing data more generally, then this missing at random assumption becomes, a little hard to figure out. And of course, if you just think everything is missing completely at random, then you have missing at random. So that may be the best or the easiest way to think about this. With monotone patterns of missing data, it becomes easier to figure out what's going on, but we basically just discussed the attrition and panel data case, which would be the natural case where you have a monotone missing data pattern. That means that if you can list the variables so that if WIH is observed, so is WIG, where G is less than H. So in this case, of course, you can just use a sequence of conditional distributions in order to estimate parameters. And then this sequence of conditional distributions can also be drawn from to generate values for the missing data. So in other words, if you start with a variable W1 that's always observed, and then you can estimate the distribution of W2 conditional on W1, because the assumption is that the missing data are only a function of W1 values, then you can draw the missing observations on W2 from that conditional density. Okay, and that becomes essentially a single imputation for that value. And then you can do it again, and you can come up with 5 or 6 different imputed data sets in that way. And the reason this sequential structure is useful is because then you can go on to the next variable or the next time period and do exactly the same procedure, where now you use the imputed data that you just used in the previous period to draw for the current period. Okay. So let me just show you a simple way that imputation is done and the pros and cons of it. Suppose that we actually want to estimate the unconditional mean of y, and we make the missing at random assumption where the x's are always observed, and we actually know what the conditional mean of y given x is. So this parametric assumption, you could make it non-parametric, but typically this is done in some flexible way. And this is the cost of the missing data, right? Is if you want to be able to impute values for y, then if the selection really depends on just the x, then you have to use the conditional mean in order to then generate the imputed values. So we already discussed why it is that now just using the observed data consistently estimates beta. So the first step would be nonlinear least squares using the complete case data. But because we always observe x, we can then predict a value for y for the y's that aren't there. So this scheme leads to a so-called conditional mean imputation, and that would be given by this right here. So in other words, so now how would we use the imputed values in order to estimate the population mean of y? Well, we would keep y if we observe it, and then we impute the missing value using this estimate from the conditional mean if we don't observe it. And that's not right. What should be written here is from p-lim of beta hat equals beta. Clearly, this is just assuming the conclusion that I'm going to state next. So the fact that beta hat is consistent for beta means that we can replace this summation in the limit with this expected value. And then it's just a matter of invoking iterated expectations to show that, in fact, the expected value of this is equal to the population mean. Okay, so imputation in these kinds of contexts is fairly straightforward. The danger, of course, is that we're going to ignore the fact that we estimated those betas in the first stage, and that those observations on y, their only uncertainty is in beta hat, right? That these don't reflect general randomness that comes from the unobservables. These are deterministic functions of this vector x and beta, and then the fact that beta hat is in there, that's just sampling error. So, as I said, that's called the method of conditional means. They also, Little and Rubin prefer, and I think does the literature in general, is the so-called method of what they call conditional draws, which is to add randomness to this imputation to the missing values, because you know that the chance that the actual data is equal to its conditional mean, basically, is very small. So what can you do? Well, of course, as you layer on more stuff, you have to make more assumptions. So if we assume that the underlying errors are, say, normally distributed, then we would just simply draw an error from this estimated distribution and then go ahead and impute a value in that way. So, of course, we'd have to estimate the error variance, but that's also consistent on using the selected sample. And then just draw from a normal distribution, and then this becomes a single imputation for this particular problem. Now, of course, now there's this additional uncertainty that's been added that isn't just, you can't just analyze this really in the context of the original data. And this is where a Bayesian approach really comes in, especially when you start looking at multiple imputations. So it's hard to, it's difficult in general to quantify the uncertainty that comes about from this. People have looked at what happens, of course, if you use this data, say, versus imputing only based on the conditional mean, and what happens. But both of these lead to consistent estimates. It's not a matter of does this give you a consistent estimate of the mean in the case that not adding this randomness on does not. That's not the issue. The issue really is in terms of estimating variances and then being able to come up with a sensible standard error, say, for the estimate of the population mean that you have. And if you treat this as if it's a real data point, then you're going to ignore the fact that there really is an error on the end of it. And tacking on an error that's been drawn from the distribution certainly does a lot better. But it's limited because it only applies to fairly simple cases like this. So let me just jump ahead to just give you briefly what the general idea is here. From a Bayesian perspective, when you define parameters theta, what you want in the end is something like the posterior mean of the parameter conditional on the data that you actually observe. What imputation does is it gives you this, and if you do it several times, then what you do is you get several posterior means, but these are conditional on a set of imputed data. Okay? So again, this is this is not this is just iterated expectation. So the question is, how do you use the imputation, the imputed data sets, to come up with this object when you want to basically integrate out the imputations at the end? Well, you just basically obtain these things as the posterior means, and you have d of them, and you just average them in the end. So that's what they recommend, right? If you use a procedure with an imputed data set, you do the procedure however many times you have data sets, and then your estimate is the average. How you come up with the variance is a little more complicated because you have to account for these two sources, the variance in the posterior distribution conditional on the imputed data, but then also the variance in the posterior mean. This is, of course, a standard formula from probability. And then when you get down to it, you have two sources of variation. This is the average of the variances from the imputed data sets, and then this is usually called the between imputation variance. But these things are easy to obtain, of course. There's a finite sample adjustment, a finite, not sample, a small imputation adjustment down here. So, of course, once you're handed the imputed data set, then this becomes all easy. The hard part is in how the imputed data came about to begin with. I guess it's kind of like making sausage, as you probably don't really want to know, but somebody hands you this imputed data set, and away you go. So, as I said, like these weighting methods, there are cases where they would clearly lead to some sort of systematic bias when just ignoring the data would not. So you can't just say, oh, it's better to use the imputed data. Just like it's not always better to weight, it's not better to always use the imputed data. Okay, well, let's travel back in time a little bit. I just want to quickly talk about Heckman-type sample selection corrections because, of course, they apply to the missing data problem. And I just want to highlight a couple of issues that come up both in cross-sectional cases and panel data cases. And really they have to do with what happens if you have missing data on your explanatory variables. Or you don't have missing data on your explanatory variables, but one or more of them is endogenous in the traditional sense that even if you had, endogeneity shouldn't, when you write down a population model like this, when we first start thinking about this model, endogeneity should be defined in terms of the population, right? It shouldn't, whether there's a sample selection problem is a separate issue. So let's think of this model here with this endogenous explanatory variable y2. The z1s are exogenous, and at this level, y1 and y2, presumably at least one of them is not observed all the time. It might be both of them. It might just be y1 is not observed. It might be that y2 is only observed along with y1. Okay. So the question is, what kind of Heckman correction should we apply to this particular model? Well, I'm thinking of, let's just write down a linear projection in the population like that. Okay. This becomes more substantive because this is the selection mechanism, and because I'm calling this a Heckman-type correction, this is going to lead to some sort of inverse Mills ratio correction. Okay. So again, here are just the assumptions, and then these assumptions down here, well, you can get rid of, you can encompass them all by just saying everything's jointly normal here and independent of the z's. Okay, but of course, a weaker set suffices. So the key here is that the exogenous things are always observed, okay? Or at least that's how we're defining, that's how I'm defining the problem here. So if this setup is true, then a good way to think about this, what we want to do is we'd like to estimate this equation here. Now I've written this so that this holds in the population. Okay, so eventually, of course, we're going to see which people are selected into the sample and which people are not. But the justification for the method that I'm going to talk about really hinges on having this equation here, where because this is, well, when y3 is equal to 1, this is just going to be a linear function of the inverse Mills ratio. Okay, but there's also, of course, a formula when y3 is equal to 0 for that part of the population that we're not observing. So in this equation, the key thing is that this is actually exogenous. The z1s are exogenous. y2 is still endogenous. Okay, I haven't tried to use a control function or anything like that to try to make y2 exogenous here, and there's a good reason for that. Because I want us to think of y2 as being anything. It could be binary or continuous or, count or whatever. It doesn't matter. And so by setting it up in this way, I've intentionally left this to be an endogenous variable in this equation. But this is an exogenous variable, and so by the results that I mentioned earlier, that's why just having this basic result that if you do instrumental variables and select on the basis of exogenous things, everything's fine. Well, that means I can do instrumental variables on this equation, and I can choose instruments that are, this is its own instrument, these are their own instruments, and then presumably I have some exclusion restrictions that I have for y2. Okay. So here's the two-step estimator that comes out of this. Now we have to, of course, condition on y3 being equal to 1. So the first step is to do a probit, and in general, of course, you would do it on all of everything that you're claiming is exogenous. To make this fly, you really want two things that are in z that are not in z1. Intuitively, you need one that moves y2 around exogenously, and you need something else that moves selection around exogenously. Okay, it's pretty clear that you kind of need that. These models are always identified off of nonlinearities, but you're on shaky ground, I think, if you rely on that. Okay, and then in the second stage, you do instrumental variables, well, two-stage least squares, where you do this regression. You include the inverse Mills ratio and then specify your instruments this way. Now, the couple of points I want to make about this procedure is that this is much more robust than a procedure you might think is either the same thing or close to being the same thing. Okay, suppose y2 is always observed. Then one might think, well, why should I only use the information on y2 in the selected sample in estimating the parameters? So you might say, well, I'm going to first project y2 on the instruments using the entire sample, get the fitted values, plug them in, and then do an OLS regression where I add the inverse Mills ratio. The reason that's a bad idea is because now you've suddenly taken something that works for general y2 and basically made it only work for normally distributed y2. Because by plugging in the fitted values, you've added the reduced form error to this error, and now, unless both of them were normally distributed to begin with, the resulting thing is not normally distributed, and so you won't get an inverse Mills ratio as the proper correction. Plus, this is a lot easier because all of the standard errors are appropriate for testing whether there's actually a selection bias problem. You can just use a standard t-test after doing two-stage least squares. The other thing is a lot messier. So that's one point, is that it's not a seemingly subtle change can actually change how robust this procedure really is. The other point is that even if y2 is something that you would think of as being exogenous in the underlying structural model, if you don't observe it all the time, you really should think of getting an instrument for it. Okay? And the reason is because if you don't, then in the first stage of your Heckman procedure, you have to leave y2 out, right? It's exogenous, so you would like to put it in because you think it could probably help predict selecting into the sample. But practically, you can't do that. And so therefore, to implement the Heckman procedure as is normally stated, where you assume you have exogenous things, you are making an exclusion restriction on what we usually think of as a reduced form selection equation. And that's always a dangerous thing to do as well, right? To say that, well, the selection probability depends on Z1 but not on Y2 because I don't have data on Y2. Okay, that's one way to identify the parameters in the case where Y2 is exogenous. I think it's a fairly tenuous way to do it. Another way to do it, which is, of course, easier said than done, but is to treat Y2 now as an endogenous variable and try to come up with an instrument for it, in addition to whatever instrument you're choosing to exogenously influence sample selection. There's a discussion in the notes about how this is also important in panel data contexts where you have attrition. If you just first difference and then try to apply, a Heckman method to the resulting equation, it winds up with exactly this sort of problem, that any selection probability you use necessarily leaves out the x's or the change in the x's. And so the safe thing to do, if you can, is to find instruments for those things. Okay, it looks like I've gone a little bit over, but...